otherwise.
Yes,
I don't wanna say
okay,
anything.
we're not gonna say anything, so, okay. Well, what we have is, I have a couple of trusses. Okay, now first of all, what's the assumption in trusses?
They're static, they don't move.
Not sure I can go with that one there, okay? No, what's the truss assumptions?
Zero stress.
Not zero stress.
All axial.
Yes, which they're basically the loads are all axial, and we get that by assuming that the joints are pinned. Right? And if the joints are pinned, just pins, right, then you can't put a moment on the beam, right? Because the joint itself won't support a moment, okay? And if the joint itself won't support a moment, then the loads on the members are all axial, right? Because they have to come in and be axial. Now, there's another assumption in there, which is sort of implicitly buried in there and can be relaxed a little bit, okay? And the other assumption that's buried because of that is that the loads are only going to come in on the joints. Now, you can actually load the members and just turns it into loads on the joints, right? The beams themselves will support a moment, but it turns into simple supports at the ends, right? And so you don't actually you can, in a truss structure, actually load the beams. Though we never do that in statics when we're doing that, because we haven't sort of taught you how to do that yet. But and you can always decompose a distributed load on a beam into point loads at the ends, just like we did for any simply supported beam, and the point loads are going to be on the things on the joint that get transmitted to the other members. So the big assumption with a truss, the only thing that it differs with from a beam structure, is that the joints don't support moments. And because they don't support moments, for the most part, the structures themselves, when they deform, the members are either going to get longer or shorter, right? If the loads are axial, they're either in tension or compression, and we oftentimes know which just by inspection, right? So we model these as they're actually simpler, but we model them as beams, and then we just have, because why not, and there's a little flag that you set basically to indicate that it's a truss structure rather than a beam, and as such joints. That usually gets forgotten, and so if you see deflections, your things are curved in your structures, that's an indication that it's modeling that as a beam and a frame rather than modeling it as a truss. Okay, your answers will be significantly do this. I have a couple of truss problems. First of all, this one here, which is as simple a truss as I can get. Well, maybe not as simple as I can get, but it's close. Okay? And I do this one, of course, because we actually have one out there in the Strength and Materials lab. We have one that looks just like that. Right? So, of course, we have to model that one. Right? Because undoubtedly, you guys all worked over that in Dr. Bridges' class. Yes, I have complete and 100% faith. Actually, probably didn't. That's okay.
Yeah, I don't think.
No, I'm taking brief anyway. So we have equilateral trusses here, right? So they're all the same. They're 14 inches long and they're ½ inches in diameter. Okay, so that's what we have. So I have SolidWorks here. I'm going to model in the front plane, and as sketching I will go. Right. So what am I going to do? I'm going to start drawing lines because hey, that's fun to draw lines. Right. So. And I'll draw another line somewhere like that. Hey, that's a good line to draw. And one like that. Okay, and then I can dimension these lines.
Why does it fill in the lines?
Oh, I don't know. It's SolidWorks.
Okay. We usually use that for TIA.
Okay.
That same answer. Oh, it's SolidWorks.
Yeah.
It's
Okay. And so I like all those. Now I'm going to get some more lines here because, hey, if some is good, more is better, right? Okay. And if I try to dimension this one, it's going to go, no, 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 no. Don't do that because it's over constrained. So I've got things all 16 inches. So we felt like it. Do I have a thing that looks like our truss? Let's see. So I had what? 4, 5, 6, 7 lines. So I've quintupled the complexity.
It's messed up.
Screwed it up badly, right? Okay. Okay. So we're good with this? So we can get out of the sketch, exit the sketch. I have a perfectly fine structure here.
If you're trying to dimension something, it like moves your whole, like my triangles keep moving places that I don't know why they're doing it. Is there a reason?
Well, I usually start modeling from the origin, but
Yeah, I did that too.
it depends a little bit on which order you create them in and what it assumes is constant when it does that. So small variations in how you model it has to do things. You're going to need to dimension all but one of them, right?
But it turns
So-
yours into like right triangles.
Yeah.
It makes it, if that,
Like if I,
it then makes it a right triangle. I didn't.
Is it when you're dimensioning it, or?
No, she's, no. Maybe because you have them in the middle, your origin.
no, well, it wasn't supposed to be. It started out just like this.
Yeah, there you go. That's
Okay.
Okay, we'll play with it. Well, we'll play with it a little later,
Okay, got
just
it.
to have some fun. Okay, so we're gonna do some simulation here. New new study, statics. Okay. Okay, and so what am I gonna do? Okay, study type. I'm not. Boy, this is an interesting one. Oh, I need to cancel out of that. Sorry, I can't quite go to this study yet. I've got to go do back to my features. I have to actually go make this a solid, right? So we're gonna insert some weldments, some structural members, and I better do some like custom. Let's see, what do I have in here? Oh, I got a rectangles in here. That's no fun. I don't want to make it a rectangle. I'm gonna have to go back to something like pipe and make them small pipe, even though that's not exactly what I wanted to do. So, okay, oops. Yeah, so,
How did you select the group? Just
Yeah.
you said
Oh,
group
but you
one.
loaded all.
yeah, that's, I did not select any of them, which is why it's unhappy about me. Okay. It's just, I'm unhappy with you. Delete, okay. Okay, let's try it one more time. Insert, weldment, structural member, and I'm just gonna pick a piece of pipe here, and then I'm gonna start putting things in groups, And I can go you in a group, and 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 you in a group. And when I try to click on somebody else, it goes, heck no. And it goes heck no because it will make a loop of them, but won't make anything that branches. So if you have things that branch, what do? You make more groups. Okay. Okay. So now we have two sets of groups, and it doesn't really matter if you don't like the way they are, you make more groups. And I think it's all because of the mitering at the ends. And I don't really care how it miters the ends at all. I am not at all fussy about how it miters the ends. It does all kinds of weird things to miter the ends depending on what the criteria is. And I don't really care, because do I trust it at the ends anyway? No. No, we're going to have some other sort of structure we're designing in there. So, and I just put in pipe here because I wasn't going to go in and define myself a 1/2-inch circle for a custom cross section.
I mean, we have to do that.
Yes, you do.
But you can build it this way, make it custom,
And then go just replace it. Yes, yes, that's true. You can. See, you guys can do all kinds of clever things, because this is a clever group, right? Not like those Everett one? I mean Renton ones? UWB ones? Oh, okay, there we go, okay. So, okay, I've got structures here, pipe schedule 40, and now I can go into simulation, and I can do a new study, and I can go, okay, and I have a new study. Come on, where's my mouse? Doesn't like working on the glass. New static study, okay. And I get my study here now. I can, the parts here, I can apply material, and let's see. I'm gonna get some material. I think I made these out of some aluminum, right? Aluminium. Let's see, you guys like something like what, 2024? We're gonna go in the O condition just because, hey, might as well, right? It'll get strong. It'll get stronger. Okay, now you notice it put in the joints in here. We have the balls wherever the joints are, right? Let's see, we need some fixtures so we can fix some geometry. I'm going to make things no translation. I'm going to fix the joints. So I'm going to fix this one over here. And I'm going to make the arrows really big so that they're, everybody can see the arrows. Is that helpful? Everybody can see the displacement arrows.
How big is that?
That's big, big arrows. And then I'm going to do some more fixtures. I'm going to use the reference geometry this time. I'll
The last
pick.
one you did immovable, right?
I did immovable, yes, no translating. Right? It can rotate but can't translate. And I think I'll pick the top plane as the orientation because I want it to be, I want to fix the outer plane one here. And then I want to fix one of the others. I probably didn't choose them wisely, but let's go big arrow again and see what I did. Okay, and I'll pick on that ball there. Looks like I'm fixed them well, right? It's not allowed to move in the Y direction, and it's oh come on, stupid ball. It's not allowed to move in the Y direction, and it's not allowed to move in the Z direction. It is allowed to move in the X direction. Okay. So it looks like out of my random choice, doesn't really matter, but you got random choices. I just need I need to constrain it so it can't move up it vertically, up and down, and then it helps if it can't move out of the plane. That's probably a good constraint to put on it. We say okay, and then I put a load on it, right? I put some sort of force on it, and we're gonna put the force on the joint right here. I'm going to pick again the top plane as my reference plane. I'll pick the out of plane. I want to go in the other direction. I want my symbol to be big again because we like it when it's big arrows. So I got big arrow going down there, right? And I'm gonna make it 4,000. Let's make it 5,000. Okay. Okay. So, are we liking this? I don't know, probably. Okay. We got forces and loads on here. We can probably mesh this guy up, which means it's not going to look any different except it's got some funny lines in it now. Right? And we're going to say, oh, I have faith in this. I'm going to run this study. And it's going to go, oh. Okay. So we got answers. Looks like I overstressed my poor, innocent little 2024, which only wanted to go to 10,000 PSI or 10,000 PSI. I went to, looks like 13,000 in these things. Now, do we trust it? Do we believe? And of course, everybody knows the answer.
No.
No, yeah, that's right. We don't believe it.
It's not
It's
wrong.
we don't believe. Okay, but then the reason nobody's going to say that to me is because they know my follow-on question is why? Absolutely. You've got my prediction. My method is entirely. So what's it doing that we don't like, other than your instructor did it?
Bending.
It's bending. It's a truss, right? Is it? If it's a truss, then all the members should have axial or compressive loads. And if they're axial or compressive loads, then they shouldn't bend. They should either get longer or shorter, but they shouldn't bend. And I don't know about you, but these look like this guy does not look straight, right? It looks bent. And in matter of fact, these other guys look bent too. So what did we model this year? Well, we wound up modeling this as a frame, as a beam, right? With all the joints welded together, which is maybe a fine way to model it, but it's not a truss. Okay? So we have to tell it it's a truss. Right? So how do we tell it it's a truss? Well, in one of these things, actually I think it's in this one here, connections, right? Where's the, actually all beam select, actually that's not that one there. Where is it? No, that's just the solver stuff. Where is the, somewhere in here, there's the, no, where's the, I wanted to say it was here, but it's not in there. It's not giving me that choice. So now I have to go find out where they hid the truss thing, where they hid the truss flag, which is annoying because they buried it someplace. So where did they hide the truss thing? It's not there. Pipe is not going to be it. Yes, there it was. I knew it was in there somewhere. Okay, so if we go down, dive down through our cut list to our solid body, we can edit the definition, and there's a button that says it's a truss.
You have to do that for all of them.
I don't think there's a way out of it. I think you have to do it for all of them. They actually go through and they do go through and change the icon, so you can tell if you've modeled them as a,
Should we have the same amount of folders as we
what's that?
The pipe folders? We should, if we modeled it just like you did, we should have the same amount, right? I have less.
I have 4.
Okay, I have 4.
I think it's which group you have, how you did the grouping.
Ours also don't say SCH, ours say
Oops.
I said this stage 40.
Oh, mine said this.
Oh. That's strange.
Okay, and I think I've got them all changed now, no, and they went back to behaving as beams again, which is annoying, because I didn't remember telling them to do that. But obviously I clicked one of the wrong buttons one way along the line, and okay, so they're all trusses now, or at least we think they're all trusses. And we ought to be able to run the study. Okay.
Mine still has, my coloring is the same as yours, but mine still has like cracks in it. Like, it looks like it's not. Does yours look like that?
Yeah,
Mine looks like that.
Mm-hmm.
Okay,
Me too.
Ours look rigid, but still shifted down.
It's bending.
Yeah.
Bending?
Yeah, it's not flex.
You mean welded more.
Rigid. Just look at our screen.
Yeah.
We all.
All ours look like that.
Some more welding.
Yeah,
Yeah.
yours looks good.
Like, doesn't look like
No,
that.
It doesn't look
no,
like yours.
because mine's not behaving itself in some strange reason.
Oh.
Wow.
I
So
almost-
we're the
almost
ones
got
doing
it on
it
the
right
ground there,
this
didn't I?
time.
So, well, no, what did hers is straight now, right?
Yes.
Hers is all straight, it's deforming.
Yes.
Mine, for whatever reasons, I suspect that I edit the definition and it's showing, it's deforming, but it's not doing, when I define it, it's not doing very much. So let's do like 20 and we'll see if that,
24.
I'll try to do the displacement. It's still not. Come on, edit the definition. Come on, okay, chart options. Deform shape, I want to say automatic. I'm going to actually define. See, it's barely deforming mine. So let's do 100 and see what happens. There it goes. See,
There we go.
it's
Yours dips down. Oh, yeah.
do it. The problem is that it's, come on. What it's doing is it's, mine, for whatever reason, the auto scaling wasn't happy, right? So it deformed, it didn't do it barely deformed, right? It got the stresses, but it barely deformed. Okay. Okay. So now, are we happier about this? That's kind of what yours looks like, right? Sort of close. I mean, you got some gaps in
Yeah,
here,
yeah.
just because what happens is they're square, and when they rotate, there's
How come
right.
yours doesn't?
I have no idea.
Okay.
Okay. It's who knows what it's actually showing down at the end conditions on some sort of funniness. And then let's now one of the things we're looking at the axial in bending. Let's go ahead and edit the definition here of our stresses. Let's look at the axial loads. All right. Because that's typically what we're concerned about in a truss structure, is we're worried about the axial loads. And we look at this, and this looks a whole lot better, right? Because what do we see? We see that if I look at the axial load, what do I see? That the portion around the outside is in compression. Right, these two here are in tension, and these here are in tension, but not as badly. And that makes a certain amount of sense, because what are we doing? We're pulling down here quite a bit, right? What does it do? It puts that outer portion of the truss in compression, right? Because it's having to support that. These members here are carrying the tensile loads, but because of the angle, those outer ones want to go out, right? They want to move out, and so that puts these in tension, right? So, hey, that's easy, isn't it? Now, I kept waiting for it to break. It didn't. I'm disappointed.
What, the truss or the solid?
Yes, my model. My model is not breaking, and I'm unhappy with it. So, let's see if I can't break it.
You want to break it?
Yes, I do, badly. So let's put another force on it. I'm going to put a force up here, just because I can. And I'm going to put it in the, you don't have to do this.
Yes.
Okay, so you can just watch me do this. Okay. Yes. And come on. Right one. Yes. On the plane. Oh no, I don't want to put right plane. Let's do the top plane. There we go. Go the other direction. Make the symbol big again. And I'm going to make it 1,000 pounds. Let's make it 3,000 pounds. Doesn't really matter. Okay, so all I did was I added another force up here on this guy. Let's go ahead and run this and see if it breaks it. Oh, darn it, still won't break.
How much force did you got?
Actually, well, okay, be that way. I will make you break yet, but I'm going to have to be somewhat trickier about it. Okay, so let's make the break. How about that one? Yes, okay. Okay, it broke. There, it broke. It broke horribly otherwise, right? Excessive displacements were calculated, right? Otherwise, continue with the current settings and review the causes. Like no to solve with small displacement. Okay. So it's basically broke. Now, what I did is it broke when I put a, well, Yeah, it's going, I'm really, really unhappy here. Okay? And why is it really, really unhappy? So let's go back and hide that. So this is what we have now. This is what I made, something that looked like this. Why is it unhappy? And I'll go back and find something that makes it better, okay? So this is what we have. Why is it unhappy? Usually I can break it without having to get this carried away, but I broke it. I put a 1 pound load on it. A 1 pound of extra load. Okay, the reason it's unhappy is that we have modeled it in the plane, but we haven't constrained it to be in the plane. What's the constraints on it? Well, it's fixed over here, and it can't move. Fixed this way, and it's fixed this way over here. So it can move this way, but how about these other guys? They're not constrained to be in the plane. Okay? We assume they were in the plane, and it wasn't nice enough to fail. Usually you'll get enough rounding errors in the system to where it will fail out of the plane, because what'll happen is it'll get one little piece of force. And so what I did is I added a 1 pound force that was off pointing to the side. And what did that do? It just flipped it over, right? Went, I can't take it anymore. Right, I'm gonna flip over here and flip it upside down because it's free to rotate. Basically, this whole thing is free to rotate about these points, right? It's free to, and this is true of all trusses. And in fact, the guys who build them will point out to you and design them and put that they're only stable and they're only capable of carrying the load when they're fixed to be in the plane. Okay? And when they're not in a plane, the darn things aren't stable at all. I spent one summer putting on 60 foot long trusses where they were 30, like 15 feet tall. It's a 612 roof, so 15 foot tall, 60 feet long. And they made them in two sections. 15-foot truss you can't get down the road. It's too wide to put on the road. So what do? They make them 10 feet wide. They fit on a truck that way, and you get them down the road with oversized load signs. And then they make a 5-foot little triangle you put on top of them to get the truss. 60 feet long, 15 feet tall. Well, you have this big thing it's a trapezoid, right? And what does it want to do when you're just trying to stand it up? Well, the bottom wants to rotate one way, and the top wants to rotate the other. It wants to do this, just under its own weight. Does not want to be in the plane. And so what do we need to do is we need to pick all of the other points and constrain them to be in the plane. Now, if I forced this because the more complex one, I'm not going to model. I'm going to let you guys do it. Right? The more complex one. No, I'm not going to model it. Right? I'm going to let you guys do it. Because I'm going to give you this one here, right? Which is slightly more complicated, but only slightly. Right? Okay. Yeah, of course it's out of a book. Right? So yeah, absolutely some statics book somewhere. Okay, some convolute trap. Have people built things like this? Yes. Yes. We don't build them so much anymore because we tend to make things out of steel and then we'll let them carry moment loads rather than building them out of trusses, wood and doing trusses, but we used to build a lot of stuff this way. Well, this one you got a whole lot more members, right? So what happens is this is a whole lot more likely to go out of plane, right? To twist out of plane. So, okay? think that's gonna be hard to model?
Not long.
You think the hand calculations are gonna be tricky?
Yes.
How are you gonna do the hand calculations? Well, how do we do calculations in trusses?
Got it.
Yes, that's what we call the method of sections,
Yes.
right? There's the method of
Yeah, I remember
joints,
those.
and then there's the method of sections. And after a while, you start initially by going, why would anybody ever do method of sections? Method of joints is much easier, I'm just solving forces. And then after a while, you go, no. Once I get the moments down, why would I ever do method of joints? You have to work your way all through all the equations, all of them. It's a big pain in the neck. Method of sections, there's always only 3 unknowns, and by cleverly picking the points,
Yeah.
you can get them to resolve out. You remember this, statics,
Yes.
statics.
I don't have my notes.
Yes. Oh, okay. Well, I'll even help you out here a little bit. Let's see if I remember how to do method of sections.
No wonder.
Do you think I remember how to do method of sections?
Yes.
Oh, you're ridiculously optimistic here. Okay, so let's say we have this guy here, right? Chun, okay? And then we have what, like this? Boy, this is a fun truss. I forgot how much fun this was. It was really fun. Okay, and we've got forces. Okay, and I'm going to stop there just for some. So, let's say for the sake of discussion, we want to solve for what? We want to solve for the forces in, we want to solve for the forces in some section, right? And we always want to cut to where there's what, like 3 of them, right? We want to be careful that there's always 2 or 3 of them, right? So what we want to do is let's go through and say, okay, how about we cut through here? Okay, that a perfectly fine place to cut. Right? And so what do? Well, we cut that section out, right? Which means we have this. Okay, and I'm going to label these over here, what, some FA, FB, and FC. And then what do? And then I have F1 over there, and I'm going to put in here, because I'm going to need it, RA, well, and RAY, and RAX. Right? But we can solve for the reaction forces by just considering the thing a rigid body. Right? We just consider a rigid body. We don't worry about any of the internal stresses. Right? We're just looking at the whole rigid body. And you can do that all with statics, right? We've done that before countless numbers of times. And if you can't do it, I'm really going to grumble at you.
Super disappointed.
Yes. Very disappointed. Okay. Yes. Okay. So once we have this, what was the method of sections is we said, hey, this thing has to be in static equilibrium, right? So what do? We solve for the moments about points. And we solve for moments about points that we pick carefully, right? And we pick them carefully because we pick points where 2 of these forces intersect. Because if we pick those points then, and we sum moments about them, then they don't show up in the moment equations. Right? Right? So which point do you want to pick first? Well, what are the choices? Well, you got this one here. That's a good point, right? And you got one over here. This one's nice because these two unknowns cancel out, right? And this one's nice because these two unknowns cancel out, right? Okay. Those are probably the easy ones to pick on, right? At least to start with. Okay, and then what do? You write moments about, what do we want to call this? We'll call this point X and point Y. And you go some of the moments about X is equal to 0, and that's going to be equal to what? If we use those dimensions here, it's 1.5 meters times RAX plus FC, right? All of those, and then it's going to be and then it's minus RAY times what looks like 2 meters, right?
Isn't that a roller at F? There's no,
Yeah.
there's no.
There's
There's
no
no-
RAX there? Okay, so that's okay. That's fine. It's just equal to 0 then, right? Okay.
I feel better
So-
now. Thank
Okay,
you.
no, that's not a problem. Okay. That just means that term there is gone. Sure. Okay, yeah, you're absolutely right.
Just want to make sure I didn't forget something.
No, you're absolutely correct. Okay, so it just means that term's there, 0, so it looks like what? It looks like we have, this is, so it looks like we solve statically for RAY, so it looks like FC is going to be equal to RAY times 2 meters over 1.5 meters, right? Or 1.33. You've got one of them solved there, right? Right? Make some sense, right? Now what? We'll pick another point. Right? We'll pick another point. So we go, so what? Some of the moments about y is equal to 0. It's this point down here. And so we're going to have what? We're going to have, let's say this is going to be equal to F1 times our 2 meters. Right? And this one is 2 meters. And then we're going to have minus the other ones, which is going to be FA times 1.5 meters minus RA times 4 meters. Did I get those right? We've got 3 forces about y. I've got this one here, and this one here. That 3 forces making me moments about them. This one is, this guy here has a 1.5 moment arm. This one is positive that way. That's this guy here, right? That's a 2 meter moment arm. This one over here's got a 4 meter moment arm, right? And so now, what do? We just got one unknown in here, FA, right? It's the only unknown we've got. And so we go solve for it. Right? Is that going to work? Remember our statics? We have statics nightmares? No. You've got statics. Don't you wish you could take statics over again? Wouldn't you just cruise it? It would be just like, such a laid-back class. The homework would only take me about 10% of the time that it took me originally, maybe 20% of the time. Okay. Some of it's just cranking the stupid algebra, right? Okay. But I wouldn't have to think very much. Go, oh, okay. Yes, some of the forces, hey, you break them into vectors, you add them up, yep. How many times have we done that now?
I think everybody would be ecstatic to take.
Take statics over, yeah.
Ecstatic?
Ecstatic. Ooh.
Signature
There's
by
unexpected
Rose
strength in you, young man.
He's rubbing off
Okay,
on you there.
okay. So, yes, you had a moment. Yeah.
I'm
In the-
kidding.
It
Nobody's
says-
forcing you to be here.
It says it's a
Hi.
cross-sectional area of 450 millimeters. Do we just pick if it's a circle or a square or
Yep,
rectangle?
it's a truss, right?
Okay.
Stress is F over A, right?
Right,
It
okay.
doesn't matter what,
Okay.
doesn't matter what you do, right? Because it's a truss, right?
Okay.
So because it's a truss structure, right, that all the stresses in it are F over A, right? They're all axial loads, right? So it's
Okay.
so you can pick up any structure that you want that gives you an area, right?
Okay.
Okay? Do we believe? You think you can do methods of sections? Painful. Lots of moment equations. I like moment equations. So am I expecting you to solve your truss with method of sections? Yes. I am. It even said in there using method of sections. I was really picking on you there, wasn't it? Okay. Now you could probably go through method of joints, but that's painful.
Yes, it is. Oh, yes, it is. I remember now.
Yes, method of sections is much nicer than method of joints. You're summing for all the forces each individual joint. So you got to take all the forces, break them all down into their vector components, and then you have this system of equations with as many unknown forces as there are members in it. That's a big pain. You want to do that? For how many members do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15? 15 equations? No, 15 unknowns? No, that's ugly. You'd have to have 15 equations. Who wants to do that?
Yeah,
No,
Majas.
no, no,
Yeah.
no. Just say no.
Yeah.
Right? Just say no. Would that be evil? If I said method of joints there, then you could say real nasty things about you. So, you think you can do this one here? Okay.
Where would you?
See.
Okay.
Okay. Now, so, and yeah, we could be slightly more creative about those if we wanted to. Like you could do something that was slightly more creative. Yeah, you could play some slightly more creative games. And I have faith in you, right? I have faith in you. So, yeah. Like the only requirement is that you cut 3 of them, right? So you can do some things like you can go, oh yeah, I want to go through here.
Wait.
Hey, why not?
Let's do 3. Let's do 3.
Yeah. Okay, so anyway, the requirement is you gotta do the statics first, though. You gotta do the reaction forces first, because we got RA showing up in there.
Did you just say we only have to check 3 of the members? Or we have to do all of them?
No, well, you probably had to solve the truss, or at least most of them. Right?
Okay.
Some of them may be pretty easy. It's okay, so I said I wouldn't give you a midterm.
There, bud.
No? Said I wouldn't give you a midterm.
This is our punishment? Is that what you're saying?
No?
Oh, there is a butt. That is a butt.
That's a butt?
This is our senior project, right?
No.
What is that?
Oh, do we have a project and a final project?
design project. Okay. You should get used to those by now. We had them last quarter, right? You think I'm gonna not give you design projects? Okay, you remember the page, yes. Well, see, that's after a while you get a new right? Ah, yes. This is the footbridge project. You're going to design me a footbridge. I actually have a let's see if I can find it. I'm going to have to go off and see if I can't. I actually yes, let's see where I have. Oh, come on. I don't want that. View. No, it's not there. Okay, I guess I have to do this one. I thought I had done a better one than this, but that's okay. Okay. So, okay. I have to tell you, see, I get bad stories. So I got carried away years ago and have a carport at my house. So that had a little deck out in the middle of it. Okay, so you had a little deck out in the middle of it, and I didn't like the little deck out in the middle because, first of all, there was this funny fence, and you had hot mop all the way around the outside, so like 4-foot border. So I got carried away and built this deck out here a little bit more. And the reason, it's got a pretty fancy railing, but big reason I didn't like the deck was that it's a carport. It's a carport like this. So how do you get anything onto the deck? Well, there's a door in the house that goes out onto the deck, and the door in the house, so that means your barbecue and your picnic table and everything else has to get drugged through the house, right? Which is, shall we say, not acceptable, right? It's frowned upon by domestic partners, and I will say frowned upon by me, actually. I don't like dragging my stuff through the house. So, well, what do you do with a deck that doesn't have any way to get to it? Well, you build a bridge. Okay, not exactly decisive. So what do we have? We have a deck, right? And then, okay, over here, by the way, it was 3 years worth of work to get the retaining wall blocks up to where you had to do that first because they are, after all, are supporting the bridge. So, okay, and then of course I have to go structurally beef up the carport for that. But anyway, I had it wound up with a footbridge, right? So now you can walk up to the deck. It's civilized people, right? And don't have to go through the house. There's a door back on this little bay out over there. There's a door that sits out over there down the driveway. So okay. So anyway, that's where the madness comes from, right? And so I thought, footbridge. So now how did I make my footbridge? Well, I don't have any really good pictures of it. It's probably best back here. The footbridge, it's just some steel. Right? And it's steel tubing. Now I use steel tubing because, hey, it's not very long. In some ways it's easier to work with than I-beam, right? It's not quite as efficient, right? Because I-beam is more efficient for beam because the weight is, there's not really any torsion load on it, but hey, it was easy enough to do this. So anyway, I built this beam, this thing, put this and of course then you have to support the flooring material. And so I said, okay, well, we'll just, in this particular case, it's those 12-inch, 2 foot by 2 foot concrete paving stones. So that, so the maintenance is non-existent, right? Are they gonna rot? No, not gonna do anything. So anyway, I did this, and this led to the dreaded bridge design project. So I thought, hey, it'd be fun to have my FEA students who need a design project, it'd be fun to have them design a footbridge. So I went out and explored the criteria for footbridges. Okay, design criteria for footbridge. So here's our design criteria. Footbridge, our bridge is 36 feet long and 6 feet wide. Okay, it's a nice, big, fat footbridge, right? Okay. You don't want them any wider than 6 feet because people drive cars across them. And then this 6 foot wide, the only one to get his car across is Taki.
Yeah.
She's doing it.
I would.
So, okay, so, okay, it's, so we're gonna build a footbridge, it's welded together. You're gonna weld the footbridge together, they're gonna put it on a truck, drag it out there, take a crane, drop it in spot, okay? That's how they like to install them these days, okay? Hopefully they get the boom truck there and just drop it off. Okay, it's 36 feet long, 6 feet wide, and it has 2 criteria. You need a point load of 1,200 pounds anywhere on the bridge. Okay? And then a distributed load of 50 pounds per square foot. Okay? The 50 pounds per square foot, let's just think a little about where those come from. The 50 pounds per square foot assumes that each individual when they're standing up is going to take a 2 foot by 2 foot square. Right? That's sort of personal space, right? Minimum personal space. You know, 2 foot wide, that's 200 pounds. Probably not bad. Hopefully most of you are under that. Some of us like me are not, but that's, I don't want to talk about that. So we won't go that one. Okay, so that's the sort of average weight in there. What's this 1,200 pounds? Point load. Well, footbridges, people aren't the only things with feet. You have animals. Okay. And so animals are small animals. Okay. No, we're having 1,200 pound animals. Cattle, horses, right? Usually on a footbridge, depending on where it is, it'd mostly be horses. Cows, amazingly enough, are smart enough where they'll go around them. And if you have a mule, it's usually smart enough to stay the deck, it's off the footbridge. But horses are not the world's smartest critters. It's sort of bred most of the brains out of them. So. I had my horses in my younger days. That was yes. Don't let me go there. So okay.
Now you have mules. Is that what
no, now I have. I spent the last 40 years removing all the fences from my property that would constrain large 4-legged animals. So because been there, done that. Don't want to do it again. So that's that. Other people can have fun with horses. I'm not going to. My sister and my mother and all are still very much in love with that, so I have to avoid it. Okay, so but basically, if you count the loads, the other constraints, the deck weight is included in the distributed load. Okay, the weight of the deck is included, but in order to carry the load of the decking, you can't span any more than 18 inches. The decking cannot span any more than 18 inches. So you have to have some structure there that's gonna carry, at least carry the load of the decking. I don't care which way you run the decking. If you wanna assume it's planks, that's a fine thing. Usually is planks. I don't care which way you run it. Whether you run it lengthwise or horizontal, it's oftentimes run either way works, okay? Okay, it's probably more traditional to run it crosswise, but people run it the other way, and that's certain, there's nothing wrong with it, okay? So you don't need to model the deck or the railing. So I'm trying to make it easy. The only thing you need to model is structure. Structure, okay? Structure, but your design needs to be able to think about bolting on the railing, because somehow you actually have to attach the rail. Okay, you actually have to attach the rail somewhere along the line. Right. Okay? So you design the cast, safety factor for yielding of 9/5. Manufacturing cost of the bridge should be minimized. Okay? Which means, when I say the manufacturing cost of the bridge should be minimized, what does that mean? KISS. Right? Keep it simple. Okay? Do I expect big elaborate trusses? That's your, you're gonna be one of those, aren't you? Okay.
Titanium and
Okay, yes, yes. One of those. Okay. That's okay. I have. I'll give up using the roller point and go to the big felt tips. Okay. Okay.
just for mine.
Those big red felt tips, they're easier that way, I don't have to do. Okay, so, right, okay, so basically, right, basically a footbridge, 36 feet. Well, you can buy steel sections in up to 40-foot length. They're readily available up to 40-foot length. So it's not a problem of making it out of one steel beam. Would I encourage you to do such thing as make it out of things that are 36 feet long?
Mm-hmm.
Yes. I would encourage you to do such things. Okay? So, because that would be simple. Okay? Oops. Wrong. It doesn't work when I'm seeing, trying to treat it like it's a PowerPoint and it's a Word document. Okay, so you need to give me a short written description of the problem, an FEA analysis of the design with your loads and your boundary conditions. Where do you put the worst case load? Because you got a point load on there, where are you gonna put it? Right, where it's all worst case, right? We need stress plots for them. And if you have any notable stresses that are over the design criteria, any stresses that are exceed the 9/5, need a little explanation as to why. Okay? It may be that they're in a boundary condition and you don't believe them. I'm okay with that. But okay, a drawing, not a complete. You don't have to do a drawing package, but at least enough of a drawing to sort of lay it out and have some hope that and a bill of materials. Okay. There's another project too.
There's a final
3 weeks.
Is this the problem?
The final is what? What
This is
about the
due
final?
in 3 weeks?
Yeah.
Okay.
This is
But wait, when is the
No.
final due? In 3 weeks?
I'm so confused.
So when do we get the final?
The final is due,
We don't have final, this is final.
yes, no, this is not the final.
So this is due on the
It's a
6th.
nice try, but it's not the final.
Due on the 6th.
Okay, so, yes,
And final.
The final's due the next week.
yes, so let's see the calendar, find the calendar here.
Projects at the same time.
No, you'll get done with them, right? 1,
Work
2,
together.
3, 6, so, I'll probably give you the final on the 6th.
Oh, wait, on the 6th?
On the 6th.
And then
Yes.
due
No.
And it'll do the 6th, do the 15th.
So
So this is due when?
this is due on the 6th.
On the 6th.
This is due on the 6th?
And I may give it to you, I may get the final up to you on the 30th if I get that. Then you'd have 2 weeks. So I would not hesitate with this one.
Yes.
More work. That's what I get for giving you easy projects. Easy, I should have given this to you last week.
That would have been nice.
I don't know about that, that's not
In fact, I
The
think I
ones
was
you wanna-
expecting it last week.
Yeah, I should have given it to you last week, I forgot. Can't get good professors.
So the final is gonna be from the 6th to the 15th?
That's currently, maybe from the 30th to 15th.
Okay.
Depends when I get down. It's an easy problem though. That's what everybody says.
Is there, so
Is the
bill of
instructor
materials,
talking?
is there a preferred bill of materials from anywhere, any catalog, anything at all?
It's just material. You don't have to get prices.
Okay, perfect.
No prices.
Good.
I don't want 14 people calling the suppliers up going, what's the price of this or that or the other thing, when we all have no intention of buying it, right? So no prices, right? Just, I don't really care about availability, but it does have to be standard steel cross sections. You start having me weld up things, then I'm gonna go, manufacturing, what part of minimizing the manufacturing cost was I? If you're gonna say, take a big block of steel and machine me a custom I-beam, I'm going to also say, what part of minimizing manufacturing cost was I not clear on? Okay, so this is not a Boeing project.
That was good.
Unfortunately, far too appropriate, right? We've all seen the gold-plated, well, yes, step stools.
Toilets.
Toilets, okay. No, I haven't seen the gold-plated
Yes, they do.
toilets.
Yeah, that's
Okay.
okay. I have a question.
Yes.
But it's on 7.2, something.
Okay, okay. This one over here, I can go back. I can multitask. Yes.
On the structural member.
Uh-huh.
Type
Yes.
is S section or ST section?
Cross-sectional area, 450 millimeters.
Well, it's steel, but I don't know if that's S section or ST section inside the drop-down screen.
It's just steel members with a cross-section of 450 millimeters.
In the program.
Oh,
For the materials.
Yeah.
Oh,
Under weldment, under structural member,
yeah,
under type,
right.
S section or ST
For this
section.
one?
Yes. I don't know what is S
No, this,
steel or
what you
ST
need,
steel? What is it?
something that's 450 millimeter area.
It's a custom.
It's a custom
Got
one.
it. Okay. What is S versus ST then?
The S's are I-beams with tapered inner flanges.
Okay.
Okay, and I'm not sure what the ST sections are.
Okay.
I'm not sure what the ST sections are. The S sections themselves were what we used to call I-beams before we made W sections. The
Okay.
W sections are technically wide flange beams, but really they're not necessarily any wider than the S sections. But the W sections, the webbed thickness, the flange thickness and the webs, but in particular the flange thickness on the edges is constant. So they're constant thickness. And they did that because originally they were not able to roll in a set of rolls the flat constant thickness is at 90 degrees. They actually wind up rolling them when they're bent a little bit to get them thick and then bend them up. At least that was my understanding of the process. I'm sure other people have different processes. I mean, people have been rolling steel for, well, a few hundred years, right? So, actually, it's getting close to that, right? It's going to be a few hundred years, a couple hundred years. Steel is really 1800s, right? Early 1800s when we first start seeing steel in reasonable production volumes. Right, before then it was all cast iron and because didn't get, it's hard to get steel, you have to get rid of the carbon out of it, and that's, you gotta, it's hard, you have to work at that to get the carbon out of it. Okay, good people. That was an easy one, wasn't it?
It's not too bad, actually.
I got nice dirty looks from everybody. I think there's uniform hatred in the class for your professor. I can live with that. Okay, well, hatred may put too strong a word. Okay, frustration, annoyance, despair. Okay, I was hoping not to go that one there. Clancy. Is my professor trying to drive me to drink, or insane?
Trying to do that.
Hard to tell. So yes.
Anyway.
Okay.
I have a question, but it's on my screen. It's separate.
Okay, okay. Well, if there, any questions on the rest of it before I go?
Oh, I was doing.
I turned in one of those. I need to finish this.
Put it in the magical place.
So you have to build a folder structure.
You have to build the structure for it. Now, the first thing you have to do is you have to save it as a library part and get out of it. You have to exit the sketch before you save it as a library feature part. So you have to save it as a library feature.
Basically, create computer reading requirements.
So, where,
Okay, well,
structure is.
So remember that.
where you put it.
Yes.
That one.
Okay.
No, I don't know where.
Okay, where it is in the file tree,
I was thinking 3.
okay, is it's under, we'll go all the way back to local disk,
Yes.
okay,
Program data, right?
program files,
Program files. Okay.
okay, and then there's SolidWorks Corp,
Okay.
SolidWorks,
I don't feel like
Oh, you're trying
What are you gonna do?
language,
Okay.
Oh, the
English,
Okay.
development.
weldment profiles.
Okay.
And that's where you start the directory tree. And now you have to create at least 2 folders down.
Under custom, you have to
That's
put in
custom.
Sometimes
Yeah.
that's what's in the custom.
one that says
Probably should be another
rectangle from last.
Rectangles, and then under that is, that's where it needs to be.
Okay.
Okay?
Very good. I need to remember this spot.
It's a hard one to find, and I have to go back and re-remember where it is every time.
Yeah, I pinned
Okay.
it this time. Yeah, I forgot to do that last week. Thank you.
Dr. Meek?
That was a huge gap.
Yes, if you don't know where to put it, you're doomed.
Yes.
You're completely doomed. So,
That's
this-
why I didn't
yes.
remember the profile.
Yes.
Okay, thank you.
What were you saying about, with that second problem, about the additional constraints you need? So you don't get that, when you run the study, it won't give you the error message saying it's not.
Yeah, you
proper.
need to fix them in plane. So I'll go back and do it, right, because I didn't do it here. What do? Is we have, these 3 joints have no constraints on them,
Yeah.
right? So what can happen is they can come out of the plane. So
Okay.
what you do is you need to do another fixture, and we'll do the advanced, or we'll use the reference geometry, right? And I will do is I'll fix them so they can't come out of the plane. So I'll select the plane, I select the front plane, and then I go through and fix the out of plane one, right?
Okay, I tried that.
And then you just get that one, and that one, and that should do them all. Right, and if I go back and do this, edit it to get my, I need to edit the definition and make my symbols big, because I didn't get the big, I didn't get big arrows, right? Okay. And now if I look at it, see I got my symbols here. And it was not running before, but if I run it now, it'll run. See, it runs fine.
'Cause I did that, so I made the other one, the bigger one, and put the regular, I guess, roller and the other constraint. And every other joint, I added just one.
Coming down the back, yeah.
And it's still.
Well, let's look at what you have there.